Hi everyone, welcome back. This is the second part of the lecture on fracture mechanics. We'll continue on with defining what the conditions are for cracks to propagate, leading to failure. Where we left off last time was with the concept of stress concentration as it applies to flaws which can occur in a material. These flaws cause the stress to increase fairly dramatically near their edges, concentrating the far field stress, that is, the stress far away from the flaw, up to some maximum point at the flaw's edges. We know that when this is taken to an extreme, such as a crack which has a very small tip radius, the stress concentration factor doesn't make a whole lot of sense anymore, as the maximum stress approaches infinity. What we can do is look at some characteristic length ahead of the crack, which avoids the singularity. The stress locally around a crack is proportional to how fast the root of this distance changes, or that is, the local stress is inversely proportional to the proximity to the crack. What would be very useful is to have some way of stipulating the length of the crack with respect to the stress that can cause fracture. And that is what we're going to cover right now, along with the utility of the stress concentration factor. As we know, the stress at a microscopically sharp crack tip is extremely high, and moving outwards, a region must be above the yield stress, and therefore encountering plasticity. A bit further out, it's back to elastic, and that will be a focus for our course. This approach for treating cracks as being dictated by elastic behavior is known as linear elastic fracture mechanics, and is an excellent place to start when assessing what cracks will do. This approach assumes that the elastic zone that surrounds a crack is much larger than the plastic zone. Therefore, we'll need to set some bounds on when and where you can use linear elastic fracture mechanics and the material properties that are used within this framework. We know that a far field stress acting on a crack of a given length can be related to a stress intensity factor, K, through a proportionality. So it stands to reason that if we want a material property, all we need to do is put some stress on a predefined crack and we can get a K, and therefore come up with some engineering values as to how susceptible a given material is to fracture. Here I've drawn a more realistic depiction of how stresses concentrate around a microscopically sharp crack. Specimens that are used to assess fracture properties are designed such that the elastic region is always larger than the plastic, and therefore there'll be a zone surrounding the crack where K can be assessed elastically on a linear basis. These specimens are called compact tension specimens, and the geometry of them is carefully designed to make sure that this is the case. This is what happens when you pull one of these carefully designed fracture specimens apart, showing one half of each side of the specimen for a material with some ductility, as shown on the top, and brittle on the bottom. For the brittle material, the failure surface is perfectly flat right across the specimen. For the ductile, there are lips that appear on the edges, but the surface is mostly flat in the center. The cause for this type of behavior is down to how plasticity can affect the test results. Even though the crack goes through the entirety of the specimen, and it might seem as though it might behave uniformly all the way through, it doesn't. This is because the crack is constrained differently by the amount of material that surrounds it. At the center, there is more material to carry stress, but on the periphery, there isn't any. There are engineering terms for the stress state that occurs at the center of the specimen versus the outer surface, which is a plane stress. All the stresses occur on the plane XY, and plane strain. All the strains occur on the plane XY. You'll encounter these terms again in further mechanics courses. The takeaway here is that there is more plasticity that occurs on the surface rather than the midplane of these compact tension specimens. But why is this important? Well, if we want a material property, that is, something that doesn't change regardless of how much material is being considered, then it makes a big difference. This is because if the thickness of our compact tension specimen isn't large enough, it can affect the stress intensity factor K. For very thin specimens, the K is very large as the fracture is dominated by plasticity. The thicker the specimen is, it moves away from this condition to a point where a state of plane strain is achieved, and the K drops to some minimum value. This is the basis for the material property of fracture toughness. It quantifies a material's resistance to crack propagation. It is assessed by specimens that have adequate thickness to ensure that a minimal value is obtained, so that it is universally applicable to all loading scenarios while remaining conservative. That is, if your component is thin, then there will need to be more stress required to open the crack because it will need to plastically deform. Note that there is an equality now versus the proportionality for the stress intensity factor as used previously. Some constant times the far field stress times the square of pi times the length of the crack. If we were to take our compact tension specimen with a known flaw length A and apply sigma stress to it, and it fractures, then the K1 achieves is equal to K1C, or KIC. The K in the mode 1 direction. The I in this case is a Roman numeral, and C for a crack. While called generically the fracture toughness, it is actually the plane strain fracture toughness, as it is the value that is obtained under plane strain conditions. This is the entire premise of fracture mechanics. Applying conditions to a material that contains a flaw under carefully controlled conditions to identify the pattern of stress and displacement near a crack tip such that one can assess whether those patterns will cause the material to fracture in service. If the stress intensity factor obtained in the lab, denoted by Ka, is exceeded in service by the factor denoted by Kb, then fracture occurs. The stress intensity factor K is a characterizing parameter that dictates the elastic field that surrounds a crack tip. And if it exceeds the fracture toughness, then somebody's going to have a bad afternoon. More specifically, KIC is the critical value of Ki, the stress intensity factor for opening, which will cause the material to break under plane strain conditions. Like other properties of metallic materials, it will change with temperature and anything else that causes a material to exhibit diminished ductility. Before we're ready to start applying plane strain fracture toughness, we need to clear up one small detail. The constant Y, which turns a proportionality between stress and the crack size into an intensity factor. The true nature of what Y actually does is beyond the scope of this course, but for now you can treat it as a constant. For the two very specific conditions given here, where the crack is oriented orthogonal, i.e. perpendicular, to the far field stress, Y will be slightly different. For a through thickness, i.e. the crack goes all the way through the material, crack with an internal flaw, that is, it has two crack tips, then it will be equal to 1. For a through thickness edge flaw, that is a crack which opens from a free surface into the material, then it'll be 1.12. Y relates the orientation of the flaw relative to the orientation of the stress being applied. So if a component with a complicated load being applied to it had a characteristic crack which caused fracture, then one could use the Y calculated from such an event to assess a different material, and therefore a different fracture toughness, or a different stress level to indicate whether failure would occur. As a result, with the fracture toughness material property known, one can perform all kinds of assessments. If the stress and length of a crack is known, such as for our compact tension specimens, we can get the fracture toughness. If we know what the in-service stress is of our component and the fracture toughness, then we can calculate what the critical crack size will be and ensure that our manufacturing or inspection process is able to capture it. If we know what kinds of flaws are present in our component as a result of manufacturing, or have identified some unforeseen flaws after an inspection that we can calculate what stress we need to stay under in order to avoid failure, as depicted here. As long as the flaw stays below a threshold, then the component will be safe. However, there are limits, as I've described, to this linear elastic fracture mechanics approach. Plasticity enters the stage at this point. Plasticity limits this approach because if we were to purely consider things on an elastic basis, then we'd arrive at an unrealistically high stress for small cracks. This is linear elastic fracture mechanics, after all. So if the far field stress exceeds the yield stress, then all bets are off. The reality is that the longer your cracks are, the better your chances are of predicting their behavior with linear elastic fracture mechanics. If the far field stress exceeds the yield stress, then the failure will be most certainly due to plasticity, not fracture. Long cracks and stresses lower than the yield are most viable for linear elastic fracture mechanics to predict failure. So there we have it. We've covered a very important material property to know if you want to make sure that a component will not fail if there's a stress concentrator present, such as a flaw. More importantly, we cover the basis for linear elastic fracture mechanics and the limitations of this approach. The field of fracture mechanics is quite extensive, as plasticity and other factors often complicate design. There are more advanced courses which mine these depths. However, the overriding premise is that fracture mechanics enables one to assess the likelihood of fracture if one knows the applied stress and the potential length of a crack or flaw. Until next time.